The lecture today on Conversations About Geology is on the northern Rockies of the Pacific Northwest and the Sapphire Detachment. The northern Rockies' early beginning about 205 million years ago at the beginning of Jurassic began with the collision of North American plate with the Farallon plate, which caused the crumpling of the western margin sediments to form the Kootenai Arc, the eastern Klamath Mountains, and the eastern Sierra Nevada Mountains, and the thickening of the western cratonic margin of the Pacific Northwest. Next, superheated steam formed by the dehydration of serpentinite caused by the downwarping of the Farallon plate melted peridotite to form basalt magma. The magma rose into the continental crust and mixed to form andesite that fractionated into granites. These felsic magmas continued to rise into the earlier proto-northern Rocky Mountains. Finally, the granites were mechanically weak and sheared off into great slabs that traveled about 100 kilometers eastward into western Montana and Wyoming. Those displaced rocks and the deep rocks that they exposed as they moved off are the northern Rockies we recognize today. Much of this lecture comes from the text Northwest Exposure by Alt and Heinemann. When late Paleozoic time began, our region was still the partly submerged fringe on the western edge of the great supercontinent Pangea. Everything west of the old continental margin, along the western boundary of Idaho and into central Nevada, was open ocean, and large parts of the continental interior to the east were submerged under shallow seawater. The waters were separated by the remnants of the Antler orogeny, or the Antler Mountain building event that stretched from central Nevada through Idaho and into British Columbia. Offshore to the west, island arcs similar to the Aleutian Islands shown in this image were moving southeastward to eventually collide with the old continental margin. By the beginning of the Mesozoic era, all the continents had united to form the supercontinent Pangea. For tens of millions of years, the Earth had one hemisphere that was mostly continental and the other entirely oceanic. The continent Pangea was nearly divided by the Tethys Sea into two large northern and southern lands, Laurasia and Gondwana. Approaching from the west were the exotic terrains that would eventually form northern California, Oregon, and Washington, western British Columbia, and parts of Alaska. The reptiles and amphibians of the early Triassic could have roamed across Laurasia from western North America, across Europe and Asia to the western Panthalassic Ocean. Permian and Triassic saw huge deposits of red sandstone and shales accumulated on dry land throughout Pangea. By looking at the geology, we can determine the environments of deposition of these continental sediments. In no time before or since has so much iron-stained sediments been laid down. Here we see Mesozoic sedimentary beds deposited in the Bighorn Basin of northern Wyoming. Most geologists agree that the pervasive oxidized Triassic sediments indicate a warm and a dry climate. Why was the climate so dry? Most of the vast interior of Pangea was far from the ocean moist winds. Higher carbon dioxide in the atmosphere may have caused a worldwide greenhouse effect. And during the Mesozoic, the Pacific Northwest was not far from the equator, and the trade winds were blowing off of the dry interior of Pangea. This makes sense because many of the sandstone formations contain crossbeds or dunes that indicate desert environments. Most streams were sediment choked and were unable to efficiently transport sediments to the ocean. A good many of the terrestrial formations contain salt and gypsum. We're looking at the crossbedded Jurassic Navajo Formation, sandstones at Zion National Park, Utah. Pangea was relatively short-lived and had pretty much broken up into our modern continents with oceans separating them by the end of Triassic. First to separate was Gondwana that divided into India, Australia, Antarctica, South America, and Africa. By early Jurassic, Laurasia had broken apart into North America and Eurasia. The western continent margin had existed for 600 million years. It had accumulated enough sediments, 4,000 to 6,000 feet, during all those years to form a broad coastal plain and continental shelf. With the breakup of Pangea and the formation of the Atlantic Ocean to the east and the Farallon Plate on the west, the North American Plate was born. Sediments from drainage from across most of the U.S. was draining to the west. Most of those sediments were lying on oceanic crust and were banked upon the passive margin of the continent like a series of overlapping throw rugs. When the plate started moving, the sediments that had accumulated since the antler orogeny were smashed against the old western margin of North America, like pushing the draped rugs closer to the wall. The sediments were tightly crumpled into folds and thrust faults full of granitic intrusions. Geologists in Washington and British Columbia have identified the band of tightly folded rocks, the Kootenai Arc, in northeastern Washington. The Kootenai Arc may have extended southward in eastern Washington and Oregon, beneath much younger, opaque basalt lava flows. We lose track of them until the Sierra Nevada mountains, now in California, but at that time were in central Nevada. The Klamath Mountains of southwestern Oregon and northern California appear to be the detached and displaced northern end of the Sierra Nevada mountains. The collision between North America and the Pacific Ocean floor crushed the old western margin of the continent. The pushed and crumpled sediments greatly thickened the western margin of the continent, raising a broad welt of early mountains. It was the first stage in the formation of the northern Rocky Mountains. The early mountains began to arise in the Middle Jurassic time and continued to rise into Cretaceous time, a period of 64 million years. The early mountains probably resembled the Andes Mountains of South America, which owe their existence partly to thrust faults that stacked slices of rock along the western margin of the continent. We think those first mountains were about 20,000 feet in elevation. Streams carved those early mountains, creating a rugged landscape, most likely forested on the western seaward side face. The climate inland was certainly dry. Making granite from basalt magma occurs by a process known as fractionalization. As the downwarping plate reaches 120 kilometers depth, it dehydrates due to increased temperatures and pressure. The steam it produces from dehydration melts the peridotite above it. Water lowers the melting temperature of rock. The magma is less dense than the surrounding rock and rises into the felsic crust. If it rises slowly through the crust, it will rise to its point of buoyancy and carve out a magma chamber in the crust of the earth by stoping or assimilating the felsic crustal rocks surrounding the buoyant magma. If the magma stays at this level, then the mafic lava continues to mix with the felsic crustal material and forms an intermediate lava. If it cools slowly enough, the heavier mafic minerals in the magma precipitate out of the magma and fall to the bottom of the magma chamber, forming a gabbro, depleting the mafic minerals and leaving the intermediate and mafic minerals accumulated during assimilation. As it continues to cool, then the intermediate minerals drop out of and layer on the floor of the magma chamber, forming diorite, leaving only felsic magmas. The felsic magma then eventually solidifies into granite. This process is known as fractionalization. This figure is the approximate location of the early mountains along the western edge of the continent. Two major batholiths denote the area of that early mountain range: the Canuck-Sioux batholith and the Idaho batholith. Coastal sand dunes of the Namibian Desert in southwestern Africa is a close analog for the setting of the Jurassic Navajo sandstone of Utah. Details of the stratification indicate deposition in wind-forming dunes, some of which must have been about on the order of 100 meters in height. For historical reasons, geologists have long called all the granite in central Idaho the Idaho batholith. A batholith is a solidified plutonic magma chamber with surface area greater than 40 square miles or greater than 100 square kilometers. The Idaho batholith is divided into two large batholiths separated by the Salmon River Arch. Anything as common and abundant as granite must form easily. The recipe calls for starting with any rock that has about the same overall chemical composition as granite, melting it and let the magma rise until it freezes. Most continental basement rock has the right chemical composition. The radiometric age of the basement rock is 1.7 billion years old, and the radiometric age of the granite is between 80 and 90 million years old. We know the age of the basement rock because the Idaho batholith contains microscopic zircon. The melting temperature of zircon is higher than the melting temperature of granite. Dates on the zircon date to 1.7 billion years ago. Since they are relics of the original rocks, then the original rock must be at least 1.7 billion years old. Rising magma dragged along large masses of belt rock that were hot enough to recrystallize into schists and gneiss, but not hot enough to melt. Metamorphic rock is a rock distinguished by the solid state change of the mineral, chemical, and/or texture in rocks due to high temperature, high pressure, or by the presence of hot fluid, or a combination of all three. Studies have shown that the minerals that make granite can form under a wide range of pressure, so they tell us little about the depth of crystallization. However, the metamorphic rock that surround the Idaho batholith do contain minerals that register pressure and therefore depth, and can tell us the depth of the batholith. The metamorphic rock shows that the granites in the northern portion of the Idaho batholith crystallize at a depth of about 10 miles, and the granites in the southern portion at a depth of about 7 miles. In the picture, we see granites intruding into a dark schist, certainly an indicator of the proximity of the magma chamber and a depth of about 7 miles. The original proto-northern Rocky Mountains were composed of sedimentary rock that were uplifted close to 20,000 feet in elevation. Thousands of feet beneath the mountain range, molten granitic lavas invaded the deep core of the mountains. The magma displaced huge masses of sedimentary belt formations, penetrating fractures as in the previous slide and injecting bedding plains. The mechanical effect of this was like spreading far too much icing between the layers of a wedding cake. The early mountains eventually collapsed and the pieces moved east, transforming the high early mountains into the lower and much broader spread of the northern Rocky Mountains. As large volumes of magma permeated the early generation of the northern Rocky Mountains, great slabs detached from the top of the pile and moved east, sliding on a soul of granitic magma that put a lubrication or a banana peel under their passage. Décollement, from the French décoller, to detach from, is a gliding plane between two rock masses, also known as a basal detachment fault. At least 4 enormous slabs of the upper continental crust sheared off the collapsing early mountains and moved to the east into Montana and Wyoming. Two schools of thought exist about how the blocks were able to move. One maintains that some forces must shove a moving slab of rock from behind, like the collision of the Blue Mountain terrains against the craton, and the other maintains that the moving mass glides downslope under the pull of gravity, like the layer cake with too much icing between the layers and one layer slides off the other. What grieves the skids? A large mass or a large seal of semi-molten granite, some as thick as several thousand feet, could have been the surface that the slabs glided down under the pull of gravity or thrust from behind. The Sapphire Detachment is one of the 4 giant slabs that moved and formed the Bitterroot Mountains. The deep granite of the Idaho batholith and its surrounding metamorphosed belt formation lies west of the Sapphire Detachment slab. The eastern face of the Bitterroot Mountains, the leading edge, is sheared into the Bitterroot myelinite, a platy gneiss. Myelinite develops where a fault penetrates into rock so deep and hot that they flow instead of break. When the detachment fault cut deep into the hot and still partly molten granite, it became a shear zone of internal plastic flow. Think of the slabs as cards in a deck, with each card sliding onto one of its lower adjacent cards. The surface of the Bitterroot slab shows a pattern of faint parallel lines from one end of the Bitterroot myelinite to the other, about 65 miles, and the striation points east to west. The Bitterroot Valley is a gap behind the trailing margin of the Sapphire Detachment. It assumed its final shape around 50 million years ago. Several thousand feet of younger sediments were deposited into the valley. As the 10-mile thickness of the Sapphire Detachment, or 50,000 feet, unloaded off of central Idaho, the Earth's crust floated up due to isostasy to form a broad granite dome in Idaho. The Idaho dome would have rebounded up to an elevation of 11,000 feet, and the 50,000 feet of sediments from the Sapphire Detachment spread over an area of 80 kilometers wide would have depressed its final resting area 11,000 feet. Wow. The deep rocks of the northern Rockies are the granites exposed after the detachments. The shallow rocks of the northern Rockies are the rocks of the 4 detachments representing sedimentary rocks from Paleozoic, Mesozoic, and more recent rocks of the Cenozoic. A shallow depression is located along the eastern margin of the northern Rockies. They are filled with sediments that eroded from the rocks of the detachment. Some of the sediments were eroded as the detachments were still moving. In places, the detachments rode over beaverhead gravel of southwestern Montana and Idaho before it was cemented or lithified into solid rock. The weight of the moving slab crushed and sheared the hard pebbles and cobbles, leaving them looking flattened or ovate like hard-boiled eggs. While the detachments were moving eastward, andesitic and rhyolitic lavas from volcanic eruptions were emplaced along the leading edge and in some places beneath the detachment slabs. Their position is important because it shows that the volcanic rocks erupted before the slabs stopped moving and that the molten lava underneath the slabs were available to lubricate the passage of the slabs. Some of the magma crystallized into large granite intrusions that lie in the detachment faults. The rest of the magma erupted along the leading edge of the slabs and formed huge volcanic piles. Where did all the magma, the boulder batholith, and lavas along the leading edge of the detachment come from? Why is the boulder batholith more than 100 miles east of the Idaho batholith? It is hard to imagine an independent source of magma so far east of the Idaho batholith. The current working hypothesis is that the magma moved eastward along the detachment fault that carried the Sapphire Detachment slab to the east. In the image, the overthrust belt defines the eastern edge of the northern Rockies that formed during the Cretaceous period. This is the material that was gouged and pushed in front of the detachment, much like a bulldozer gouges and pushes materials in its path. The overthrust faults are low-angle thrust faults with displacements measured in kilometers, along which great slices of deeper, older formation moved over and on top of younger formations. The slices of rocks that moved into the overthrust belt are much thinner, 1 mile or less, than the big detachment slabs, 10 miles or more. The problem with overthrusts in Montana and Alberta is that we are not sure what lubricated the movement of the overthrust slabs. Most of the overthrust belt contains no granite, like what lubricates the detachment slabs. Superpressurized water could help them move, but this was an arid region during Cretaceous time. Another hypothesis is that the Precambrian rocks moved in Cretaceous on much softer shales. The belt rocks do not contain much shale, and geologists are really not sure yet how they moved. In these two images, we see the Lewis Overthrust Fault. Mississippi and Madison limestone are thrusted over Cretaceous sandstone and shales. Whatever lubricated them, the overthrust slices certainly slid east onto the undeformed high plains. Where they came to rest on the high plains, each slice is stacked on the next slice to the east, imbricated like shingles on a roof. The younger rocks are at the eastern edge of the overthrust belt, and the rocks in the fault slices become progressively older westward. So older rocks lie on top of younger rocks. As the high mountains, the detachment slabs west of the overthrust grew, they squeezed thrust slices out to the east. As the overthrust piled on top of its adjacent slice, they squeezed more thrust slices out further east. Another picture to let you know why I'm happy to live on the warmer yet more geologically active west coast of Oregon. We're looking at the overthrust belt, big cliffs of Pennsylvania and Madison limestone thrust over softer Cretaceous Morrison shale. Final look at the Bitterroot Mountains, one of the most interesting mountain ranges in the world in the Pacific Northwest because of its detachments or decollements from its original location above the Idaho batholith to its final resting place in Montana and Wyoming over a 10 million year period in the Cretaceous from 80 to 70 million years before present.